Hello dear students, in this video, let us discuss the exact differential equation of nth order. So in the third semester, you already studied the exact differential equations. So there, the exact differential equations will have the order 1, means they are first order exact differential equations. But now we are going to study exact differential equations of nth order. So in the previous semester we have the definition of that exact differential equation, right? So if any equation is derived only by the method of differentiation, so then that equation is called as exact differential equation. So here we have that exact differential equation, that is m dx plus n dy is equal to du, means after differentiation of the function u, if we got the equation m dx plus n dy, then this equation is called as exact differential equation of first order. But now the definition is same, but the order is n. So therefore here a differential equation f of d power ny by dx power n comma d power n minus 1 y by dx power n minus 1 and so on dy by dx comma y, means it is a function involving these variables, means nth derivative, n minus 1th derivative, n minus 2nd, n minus 3rd and so on up to the first order derivative and 0th order. 0th order means there is no d by dx, simply it is y is equal to a function of x. Suppose this equation is said to be exact, when it is derived by differentiation only and without any further process, means that equation has to be derived only by differentiation, we should not perform any other operations, right? Then only that equation is called as exact equation. So that is from an equation of the next lower order of the form. So here the order of the differential equation is n, because the highest order derivative is nth order, and its lower order means the highest order will be n minus 1. So therefore now it is a function of d power n minus 1 y by dx power n minus 1, d power n minus 2 y by dx power n minus 2 and so on up to y is equal to integration of phi of x dx plus c. So now it means that if you differentiate this equation, the d power n minus 1 will become d power n, means here n minus 1 is giving the order of differentiation. So if you differentiate d power n minus 1, that will be equal to d power n, and if you differentiate d power n, that will be equal to d power n plus 1 and n plus 2 and so on. And this is about LHS. And on RHS we have integration of phi of x. So if we differentiate this integration of phi of x, the result will be equal to only phi of x, which is here. So therefore by the differentiation of this equation we can get the equation here. So therefore this equation is exact, because we are getting this equation from this one only by differentiation. So therefore after differentiation, whatever the equation we are getting, that equation will be exact, right? So therefore any equation is said to be exact if it is derived only by the differentiation of the next lower order equation. Now let us have the condition for exactness of linear differential equation of order n, means how to check whether the equation is exact or not. So in the previous semester we have discussed the condition for exactness, that is dou m by dou y is equal to dou n by dou x. If that condition is satisfied, then we can consider that as the exact differential equation. There we have only two terms or two functions, m and n, but here it is nth order, means we will get the n terms in that equation. So therefore we cannot verify this that condition to this equation. So therefore here we have some different kind of condition for exactness. So let us consider the equation. Let the linear differential equation of order n be p naught d power ny by dx power n and p1 d power n minus 1 y by dx power n minus 1 and so on pn y is equal to phi of x. So let us consider that as equation number 1. So here p0, p1, p2 up to pn, these are all, and along with phi of x are functions of x alone, means they are not constants, they are the functions of f. They may be constants but they should be a function of x alone. They may contain x but they should not contain any other variable like y, z, right? Or it may not contain x. If it is not containing x means that is also a function of x, but that is called a constant function. So here these are all the functions of x. Now let equation 1 be exact. So we know that what is the meaning of exact equation, means that the given equation must be derived from the next lower order equation by the method of differentiation. So therefore here let the equation 1 be exact, that is it can be obtained from an equation of next lower order by differentiation, right? So means to get this equation, other equation has to be differentiated once. Now since p naught d power ny by dx power n can be obtained by differentiating once p naught d power n minus 1 by dx power n minus 1, means here it is n minus 1th derivative. If you differentiate this once, that will become the nth derivative. So therefore this can be derived by this one, right? So therefore assume that equation 1 can be obtained by differentiating once the equation. So let us assume this equation 1 can be obtained by some other equation which can be considered as p naught d power ny by dx power n minus 1 plus q1. We are not considering p1 here because it is q1. q1 d power n minus 2 y by dx power n minus 2, because while differentiating these the terms will get changed. So that's why here we are not considering p1, p2, p3, but the first term will not change, that will be p naught only. We will see how. So after differentiation of this one, we will get how the terms will get changed. So therefore p naught as it is, then q1, q2, q3 so on up to qn minus 1 y is equal to integration of phi of x dx. We know why we are taking integration here, because we need phi of x. So phi of x is, we can get the phi of x only after differentiating this function. So therefore we are considering integral sign, where here q1, q2 so on up to qn minus 1 are some functions of x alone. So therefore now here we have considered an exact equation which can be derived by the other equation. That equation is nothing but this one. So let us name that as second equation, and the first equation is exact, that is the standard equation of the, or standard form of the equation. And let us differentiate equation 2 with respect to x. So here we know the equation 2. What is that equation 2? This p naught d power ny by dx power n minus 1, q1 d power n minus 2 y by dx power n minus 2, and the next will be q2 d power n minus 3 y by dx power n minus 3, and so on qn minus 1 y. Here we are not considering qn because we have started from q1 and total terms will be n. So already p naught is there, So therefore that becomes n minus 1. Next, let us differentiate this equation with respect to x. Now let us consider the first term. So here we know that p0 is also a function of x, and this is also a function of x. So therefore to differentiate this term we need to apply the product rule. Now let us consider p0 as it is, the first function as it is, differentiation of the second one. So here while differentiating you should not treat this as x power n, because while differentiating x power n we can consider n into x power n minus 1, but here it is not a function, it is the differential coefficient. So therefore here the power will increase, only that much. After differentiating the power of d will increase, that is the meaning of differentiation. So now d power n minus 1y by dx power n minus 1 will become d power ny by dx power n plus, now first function differentiation, that is p naught dash into second function as it is, plus here q1 is the first function and d power n minus 2 y by dx power n minus 2 is the second function. So first function as it is, and let us differentiate the second one, and here it is d power n minus 1 y by dx power n minus 1, that n minus 2 becomes n minus 1. One power will increase, then q1 dash into the term as it is, plus next term will be equal to what? Here we have q1 and next will be q2, q2 d power n minus 2 y by dx power n minus 2 and so on. Here the last thing is, here qn minus 1 into y is there, that becomes qn minus 1 dy by dx plus qn minus 1 dash into y, and RHS becomes phi of x, because here it is integration of this one and its derivative is equal to simply phi of x. Now collecting the like terms means here d power n minus 1 y by dx power n minus 1, here also we have the same term, so that can be take out as a common in these two, means second and third term. So first term is, that is single, that is p naught d power ny by dx power n minus n. So that's why here we are not changing this p naught, we are keeping the first term as it is, and for second term we are considering q1, that is the reason. So first term as it is, then d power n minus 1 y by dx power n minus 1 is common, remaining p naught dash plus q1, because we have p naught dash and q1. Next d power n minus 2 y by dx power n minus 2, here it is q1 dash and the next will be q2. Here you just observe that the derivative of the first function and simply function q1, and for the next term derivative of this one q1 dash and the next function as it is q2. Next will be q2 dash, means the differential of this one, and next function will be q3, so q2 dash plus q3 and so on. The last term will be here qn minus 1 dy by dx is there and its previous term. So here q2, its previous term is q1 and its derivative is there, and here q1, its previous term is p naught and here we have the derivative of p naught, and similarly here qn minus 1 is the last term and its previous term will be equal to qn minus 2, but we have to consider its derivative, plus here it is only one term, so therefore qn minus 1 dash y is equal to phi of x, and consider equation 3. So now just observe that this equation is derived, right? This equation is derived from the second equation by the method of differentiation. So means whenever we got the equation by differentiation, then that equation is called as exact equation. So right now here we have the first equation, so here this is the first equation and we have assumed that it is exact, and also we have considered this is derived by the differentiation of the second equation. So when we actually differentiate the second equation, we got this equation. It means that equation 1 and equation 3 are one and the same, because the first equation is already exact. Already exact means that is already derived by the process of differentiation from the next lower order equation. Then by actual differentiation we got the third equation. So it implies that the first and third equations are one and the same. So therefore now equation 1 and 3 must be same equations, because both are exact and both are derived by the same equation, second equation. So equating the coefficients of all the differential coefficients, d power n minus 1 by dx power n minus 1, d power n minus 2y by dx power n minus 2, and so on, dy by dx comma y. So all the coefficients of differential coefficients can be compared. So in the first equation here, the coefficient of d power ny by dx power n is p naught. Here also it is p naught, no problem. And second one, here we have p1, that is the coefficient of d power n minus 1y by dx power n minus 1, that is p1, but here it is p naught dash plus q1. So therefore p1 equal to p naught dash plus q1. Similarly, here if we have p2, here q1 dash plus q2, then p3 will be q2 dash plus q3, p4 will be q3 dash plus q4, means here this is one p1 and here we will get q1, p2 q2, p3 q3, and before this we need to differentiate the previous function, that is q2 dash q1 dash, like that. Then pn minus 1 in general, pn minus 1, here pny is there, so its previous term will be equal to pn minus 1 into dy by dx, and here the coefficient of dy by dx is qn minus 2 dash plus qn minus 1, right, that is pn minus 1, and pn coefficient of y is pn, and here coefficient of y is qn minus 1 dash. So consider this, all these equations as 4. Now to get the desired condition, now still now we have not considered the, or we have not derived the condition. So to get the desired condition we must eliminate all q's. So whatever q are there, we must eliminate all the q's, and we should get a relation between only p's. So here get a relation between p's alone. Furthermore, we shall calculate q's in terms of p's, so that their substitution in equation 2 may give the first integral of the given equation. So here by using equation 4, p1 equal to this one, right, and p2, p3, we have all the p terms, but they are not in the standard form, means they are not in terms of p, because all the relations must be in terms of p only. So therefore we are going to eliminate q's from the system of equations 4. So now here from the relation 4, q1 is equal to, here p0 dash equal p1 equal to p0 dash plus q1, then q1 equal to, in terms of p we need to write, that is p1 minus p0 dash, and q2 is equal to what, p2 minus q1 dash. So already we have q1 and its derivative, q1 is there, its derivative becomes p1 becomes p1 dash, and p0 dash becomes p0 double dash. So that we have substituted here, p2 equal to this one, then q2 equal to p2 minus p1 dash plus p0 double dash in decreasing order. Here it is q2 is there, then first write 2 minus 1 plus 0. Alternatively we get plus sign minus signs. So 2 1 0, right? Then q3, q3 is p3 minus q2 dash, and here we have q2 equal to this one and its derivative p2 dash plus p1 minus p1 double dash p0 triple dash, right? p2 dash p1 double dash p0 triple dash, then multiplying with negative sign. Here q3 and p3 will be same, means here q3 is also not differentiated, p3 that is also not differentiated. Next, increasing order of derivative and decreasing order of subscripts, 3 2 1 0, and here powers, there is no differential, means that will be equal to 0 1 2 3, right? Next, similarly the last term qn minus 1, qn minus 1 equal to pn minus 1 minus, here we have pn minus 1 equal to qn minus 2 dash plus qn minus 1, then qn minus 1 is equal to, we need to shift this one to LHS. Here qn minus 2's derivative is there, so its derivative is here we have considered pn minus 1 as it is minus, here we need to decrease n minus 1 to n minus 2, then increase the differentiation, again decrease n minus 2 to n minus 3, increase the differentiation. Sorry, here it is pn minus 1, pn minus 2 dash and pn minus 3, it is not triple dash, this one is double dash, because there is the power is 0, here it is 1 2, next will be equal to what, pn minus 4, and the differentiation will be third order, right? And so on. Here finally minus 1 whole power n minus 1 p naught whole power n minus 1, because here see here q3, for example q3 is there, the first will be 3 and the order of last function, last derivative will be equal to 3, so here it is pn minus 1, then the derivative of the last function will be equal to n minus 1th derivative, and here minus 1 whole power n minus 1, because if n minus 1 is even that will be positive, if it is odd then negative. So now pn, last one, pn equal to qn minus 1 dash, so therefore differentiation of the same thing. Now here pn equal to qn minus 1 dash, already we know that what is qn minus 1. Now here we need to differentiate this one, pn minus 1 dash, then this becomes double dash, triple dash, and so on. This will be n minus 1. Here we need to increase the derivative once, so here it is n minus 1th derivative, next that will become nth derivative. Now shifting all these terms, that p's terms to LHS, then those becomes pn, and this becomes minus pn minus 1 dash plus pn minus 2 double dash minus pn minus 3 triple dash, and so on, minus 1 whole power n. Here we got n because now we got n terms, then p naught n is equal to 0, because after shifting this to LHS this becomes minus, right? So already one minus is there, then this n minus 1 will become n minus 1 plus 1, which is equal to n, and that is equal to 0. And next here again putting the values of q1 q2 so on to qn minus 1 in equation 2 we get. So here we have the second equation, that is p naught d power n minus 1 by dx power n minus 1 q1 q2 q3 so on up to qn minus 1 y is equal to that integration of phi of x dx plus c. So because we have changed all q's in terms of p, So therefore substitute all those values in this equation. So first one will be equal to p naught d power n minus 1 by dx power n minus 1. Now q1 is p1 minus p naught dash. So here it is 1, so 1 0. Next will be q2, then 2 1 0, alternative minus and plus, and differentiations will be 0 1 2 3 and so on. Then last one is here pn minus 1. So pn minus 1 dash, because here it is qn minus 1, then pn minus 1 in minus pn minus 2, n minus 3 and so on, minus 1 whole power p naught n, p naught whole power n. So therefore that is the second equation. So here into y is there. So now this equation is called as first integral of first integral of the given equation. So it is equal to, and consider this as 6. Thus equation 5 is the desired condition of exactness. So here we have equation 5. So here pn is what? That is the coefficient of y. Pn minus 1 coefficient of dy by dx, Pn minus 2 coefficient of d square y by dx square, and so on. P naught is the coefficient of nth order derivative, means n means highest order derivative, and its coefficient is called as p naught. If the equation is cubic equation, then p naught is equal to what? Coefficient of dqy by dx cube, and p1 will be 1 less d square by dx square, then p2, p3, like that it will go. So therefore pn, that n is the pn is the coefficient of y, and then pn minus 1, pn minus 2, pn minus 3, and it will come, and p naught is the coefficient of highest order derivative in the given equation. So therefore this is the condition of exactness. Here n, n minus 1, n minus 2, n minus 3 and so on up to 0, and powers, here it is 0 1 2 3, means here subscripts are go on decreasing and the powers superscripts are go on increasing, and alternatively plus and minus. No need to remember this in particularly. So therefore just if you remember the format of that equation, that will be easy to write the equation. So this is about the condition for exactness. And then here this is the first one, means here we have considered equation 1 and equation 2, and in the next step we have differentiated the second equation, right? So here differentiation of the second equation with respect to x, and afterwards comparing the equation 1 and 3, and then equating the coefficients of all the differential coefficients, then expressing all q's in terms of p. So here we got the equation 5. So that will be the condition for exactness. Then after, if this equation is exact, then substitute all those terms in second equation. So here this is the second equation, means after substituting second equation, that will become like this, and it is sixth equation. Then this equation is called as first integral of the given differential equation. Then how to solve the exact differential equation? So this is the working rule. So first of all, write the given equation in full, that is by writing 0 for the missing terms. Means suppose in the equation d cube y by dx cube is there, and directly if it is given dy by dx, means d square y by dx square is absent, then consider its coefficient as 0, means write the equation completely without missing any term. Then write the values of p naught, p1. I already told that what is p naught, coefficient of highest order derivative, then p1 1 less, then p2 n minus 2, like this it will go by comparing the given equation with the standard form. Now write pn, pn minus 1, pn minus 2 starting from highest, right? That pn means p3, p2, p4, like that, and then check the condition for exactness. What is the condition for exactness? First, that should be highest term, that is pn minus pn minus 1 its derivative plus pn minus 2 its double derivative, like that. Means we need to write the subscripts in decreasing order and superscripts in increasing order. After getting the first integral, check the condition for exactness. So here we will get this form of equation. While solving the example, we can take that. So after getting the first integral, check the condition for exactness again. Again we need to check the condition for exactness. If the first integral is exact, then obtain its integral. So here it is the continuous process, means if the cubic equation is given, so by using the first integral, that will become second order, then first order. Once you get the first order equation, that can be easily solved by using the linear differential equation or by using the exact differential equations. So here if the first integral is exact, then obtain its first integral. So this is called as first integral only, it should not be increased like second integral, third integral, like that. So it is always called as first integral. Proceeding in this way, we generally get an equation of the form dy by dx plus py is equal to q, which is solved as above or by using the solution for linear differential equation. Means it is similar to synthetic division. So in synthetic division, what we will do, if the equation is fourth order bi-quadratic equation, so by trial and error method we will find one root. Then next we will decrease the order of the equation to cubic, next quadratic. Once you got the quadratic equation, so by factorization we can get the roots of that equation. So here also same, if fourth order equation is given, so by using this exactness, that will become the cubic. Then apply the condition for cubic equation, then that will become second order equation. Again apply the condition for exactness, that will become first order differential equation. Once you get the first order differential equation, you can apply the condition for exactness or directly solve by the linear differential equation, that you know how to solve the linear differential equations. So in the next video, let us discuss examples. So after solving those examples, you will be familiar with this condition for exactness and working rule of the exact equations.